Hi there. It is Physics Coach Powers. um, what? Well, I'm still Chem Coach, but we're doing physics now. So. So, what we're talking about today in physical science is chapter 11.1, measuring motion. So, we're starting this whole physics journey now, and physics is fun. It is an awesome, awesome thing to study. It really, when I first took physics, it's when I really started to see that math came to life. That here is the true application of all the stuff I've been learning in math now just demonstrated in real life. So I hope you're really going to enjoy physics. It's yes, about motion and about mechanics. It's about so much more than that. But let's just take it piece by piece. And if you feel like math is a tough thing, the math here in physics is not really tough, at least not at this level. So you can do it. Basic algebra is what you will be tackling. And it's not too hard. Trust me. Okay, so let's talk about measuring motion, right? That's what we're going to be getting into here today. And so we're going to cover 11.1. These are our objectives: to describe the similarities and differences between speed and velocity, to calculate speed and velocity, and to interpret distance versus time graphs to determine the motion of an object. So, what do we mean when we're talking about observing motion? Well, when we talk about observing motion, we have to understand frame of reference. Every time we see something moving, it's really just something that is changing position with reference to some other object, right? And so we want to talk about that other object. We want to talk about the frame of reference. So, motion is an object's change in position relative to a reference point, and frame of reference is a system for specifying the precise locations of objects in space and time. Now, that sounds kind of complicated, but it's really not. When you see some of our examples here, you're going to be like, oh, yeah, that makes sense. Okay, so a couple other things here. Distance versus displacement. Now, if we look at this little soccer field and we see the guy runs around the entire soccer field almost, right? He has run a great distance. That is the path that is taken. He went all the way around the edges of that soccer field. But his displacement from time A to time B when he finished, that really isn't nearly as far. That displacement is just the change in the object's position. So he may have run 190 meters, but he may have only been displaced by 10 meters, right? He may have only changed his overall beginning and ending position by like 10 meters, even though his distance might have been 190 meters, okay? So displacement's the change in the position of an object. Remember, the displacement always includes direction. And so if you'll take note of the arrow here, okay, this little arrow head, that fact that that is pointing and it has an arrowhead pointing in a particular direction, that is important, okay? So when we talk about displacement, we want to talk about the direction. Distance isn't going to necessarily have that, right? It's talking about the path, but it might not necessarily have a vector, which we'll talk about a little bit later. All right, so yeah, yellow line is distance, the black arrow is displacement. Okay, so here's our frame of reference. Now, if you'll notice, this snowboarder is going up onto the rail, going back down. So you can see that this person is changing their position, right? So they're moving. But how would we know that if we didn't have something to measure them against? Okay, lots of things we could measure against here. One of them they're saying is the trees, right? The trees might be the frame of reference. We can see that his position is changing with regard to the trees, not the cheese. Okay. All right. So physics, what is physics? Well, in general, the study of forces and energy. All right. But today we're going to just be talking about a couple different parts of physics. And this is one of the most fundamental, and its speed and velocity are some of the most fundamental parts of the study of the way that things move in this case, and things don't move without force. Okay, we're going to learn about that a little bit more later on, and they can't have a force applied to them unless there's energy there, right? So speed. is the distance traveled per unit time. And so you guys are familiar with things like speed. You guys have probably talked about traveling a particular speed, right, in your car. I'm going to change my color here to make it yellow. And so you might have said something like, yeah, I'm traveling, 25 miles per hour. You may have seen it written that way, MPH, right? That is a distance traveled per unit time. What's the distance? The distance is 25 miles, okay? And what is the time? 1 hour. So if I traveled 25 miles in 1 hour, I would be traveling at a speed of 25 miles per hour, okay? Velocity adds one extra thing to speed. It adds direction to speed. So if I want to tell you my velocity, I'm going to tell you something like, oh yeah, I traveled 25 miles per hour. And then I'm going to tell you the direction I traveled, east, okay? Or maybe I traveled toward the stadium, all right? Both of these would be an example of directions, right? I'm traveling in a particular direction. So velocity is going to include a direction. Speed does not include direction, okay? So if we ask you for velocity, make sure you include a direction in it. And I keep giving you 25 miles per hour because that's kind of what we're used to. But remember, we want to do things in the metric system, and in the metric system, we typically use meters per second. All right, so remember that velocity is described relative to a reference point. And so if I'm describing my direction, I have a reference at which I'm describing the direction to and from, right? And I can talk about going in a positive direction or a negative direction. So if I go in this direction, I might be talking about my velocity being positive from my starting point. But if I travel in this direction, I might talk about my direction being negative because it's going in the opposite direction. Okay, so just keep in mind that because velocity has to do with direction, then we have to deal with these things. And if I have an exact amount forward and the exact amount back, if I go here, boop, and then I come back boop, to my starting point, all right, so I went there and then came back, then although I may have had a speed at some point, my net velocity, because I have a net distance traveled zero, is zero. So my velocity would actually be zero at the end of this trip because I traveled in one direction and that was my positive value. I traveled in the other direction, that was my negative value, and so my net distance is zero. By convention, going up is considered positive and going right is considered positive. Kind of like on a graph, if I'm going left or if I'm going down, then we're going to go ahead and consider those negative. Okay, that's just a conventional way for us to represent those things. So to the left and down are negative, and then to the right and up are positive. Now, I can also have a combined velocity, which is going to be the combination of a couple velocities, and these are called vectors. So if I move in this direction and then I move in this direction, I can create what is my net movement. It's kind of like a combination of those two, right? It's this arrow here is basically the combination of those other two arrows. Let me change my color again so you can kind of see. So my net change, that's my vector path, is an addition of those two motions. Okay, I move this way and I move that way. Well, my net change is in that angled direction. Okay, so those combined velocities are a resultant velocity. You'll hear us oftentimes talk about vectors, and if we add these two motions together, then we have a resultant vector, which would be that diagonal arrow. Okay, all right. Let's go on. So average speed or velocity, what units do we use to represent that? Well, you can see that we have distance divided by time is our formula here, right? That's our distance divided by time. Distance is traveled in meters and time is in seconds in the metric system. And so our SI unit for speed is meters per second. Velocity would also be meters per second, but we'd include a direction. Now remember, there's a difference between constant speed and instantaneous speed. Constant speed would be something where I'm consistently traveling the same amount of speed in the same amount of time, okay? I cover an equal distance in equal amounts of time, and I'm continually doing that. That would be constant speed. However, I could give you a strange path where I'm like speeding up and then I slow down, speed up, slow down, speed up, slow down, speed up, slow down. I could have something where I'm going fast and slow and fast and slow. Well, instantaneous speed would measure whatever speed I was traveling at that particular gap of time. All right. So if I started really fast here, in this little part, then I might have a higher instantaneous speed. And if I slowed down there, it might be a slower instantaneous speed. So we have instantaneous speed being a speed at a particular given time. So let's see if we can do some of these problems. I'll do one here and we'll see how you do. All right. So calculate the average speed of a race car that in 5 seconds travels 400 meters from the starting line. Now, remember that we want to show gems, right? So we've got to show our work here. So we got to show our gems. Remember, given, right? That's the G. And so let's talk about what we've been given. We have a distance of 400 meters. We have a time of 5 seconds. And it says to calculate the average speed. And what is our unit going to be? Our unit is going to be in meters per second. Okay. So now let's do our E. What equation are we using? Well, we've just learned the equation velocity equals distance divided by time. Okay. You could also write that as speed equals distance divided by time. You guys may have done this in math, and in math you may have noticed that we do rate equals distance divided by time, right? So all of these things are basically the same, but some slight differences, right? So velocity includes the direction, speed and rate do not. All right, so that's my E for my gems. My M is manipulate. Do I need to change this formula? Well, I'm looking for speed, and that's what we have here. So no, I don't need to change the formula, so I don't need to do the M part. And then my first S is to substitute. So let me substitute these values in. I've got speed is equal to distance, that's 400 meters, divided by time, which is 5 seconds. Plug it into your calculator, right? And then we can do our second S, which is to solve. And 400 divided by 5 is going to be 80, right? So we've got 80 meters per second. Now, what about our significant figures? I have one sig fig here and one sig fig here, and I have one sig fig here. So my final answer is all good. I've just got one sig fig for everything there. And so that's how you would do a problem like this. All right, now you've seen it. Do you think you could do it yourself? Well, let's find out here in a second, but let's go ahead and do another problem in which we're solving for time. So we're solving for a different variable. Okay, again, got to start with our givens, right? And so we have distance is equal to 132 meters. And now we've been given velocity, and it's 7.3 meters per second. And we can just say toward the tree. Now we're writing that out because we want to remind ourselves that we are given velocity. And then we are trying to figure out the time. And so that equals question. And since we were given seconds here, then we know that we've got to solve and come up with seconds. Our equation is the same one we just dealt with, right? But in this case, we're going to be dealing with velocity. Let me just scribble that out. Let me see if my eraser works on this thing. My eraser work? It does. I'm so happy. All right. So our velocity is equal to distance divided by time. Do we have to manipulate this? Yes, because look, they want us to solve for t. So we have to rewrite this equation in the form that solves for t. We've got to multiply t by both sides of the equation and then divide v by both sides to get our answer. So time is equal to distance divided by velocity. So now let's plug it in, substitute. Time is equal to 132 meters divided by 7.3 meters per second. All right, so now we go on to that next step. We divide those two out. Oh my goodness, let me get my calculator out real quick. And let's see what we get here. All right, 132 divided by 7.3 is going to give us 18. So last S step here. We've got 18.08. And then our values, our meters canceled out. And so we've been left with seconds, right? Seconds. Now, we can't leave it like that, right? Because we have 3 sig figs here, but only 2 sig figs here. So our final answer has to have 2 sig figs. So we just have to say, eraser. We just have to say 18 seconds as our final answer, okay? So this is how you would do a problem in which you are solving for time. Okay, now really quickly, I want to show you my M step, that manipulate step, because a lot of you have not done this M step before, and I just want to remind you how we would manipulate a formula like this. If we start with T equals D over V, the rule in algebra says that if we do something to one side of the equation, we have to do it to the other side. We can do a lot of different things, but we have to do them to both sides of the equation. So if I want to get V over on this side, I'm sorry, let me start over again. I gave you the M step answer, and I started with that. Try again, folks. All right, so I'm starting with the E step and getting you to the M step. My V is equal to D divided by T. And so if I want to get and solve for T, I'm going to need T to be on its own on one side of the equation. I also want it to be on the top of the equation, right? On the numerator side. So whatever I do to one side of the equation, I do to the other side. So if I multiply T by this side of my equal sign, then I can multiply T by this side of my equal sign. Now, when I do it on this side, it cancels these guys out. All right, so now I have my formula. If I were to rewrite this, I would say, oh, well, D is equal to TV. All right, well, I want V to be by itself. And so I need to, I need T to be by itself. So I need to divide both sides by V now. Okay. So now I can get V on the other side because whatever I do to one side, I do the other side, and I canceled those out. And so now what am I left with? I'm left with this little portion right here, which basically is T is equal to D divided by V. So now you can see how I got that step there. It's just basic algebra. I have to go through two little steps where I am trying to isolate the T by itself and also get it up into the numerator side. Okay, so that's what we do in those cases. Now, I think you can do this one. So I want you to pause and practice. Notice that this time we are trying to solve for how far. And so now you're solving for the distance. And so you're going to have to do a little manipulating. But why don't you pause and practice, and let's see how you do. And we're back, right? Okay, so we've got this value of 100 meters per second. We notice that this has got meters per second. That's a speed, right? So that's our velocity. We're going to just go ahead and put it under velocity. It may not necessarily have a direction. In this case, you know, he's traveling down, right? We would assume if he's jumping out of an airplane. And so we could say, okay, the velocity is 100 meters per second down. And she falls for 30 seconds. That's our time. You just got to look. Okay, what is seconds? Well, that's time. All right, well, that fits into that spot. And then how far? When we want to know distance, that's how far things are, right? And so since we dealt with meters up here, then the value that we're looking for is the question mark number of meters. So now we get to do our E step. And our E step is velocity equals distance divided by time. And now we have to do our M step. We have to manipulate so that we're solving for D. Well, that's pretty easy because D is on the top already on its side. So let me just multiply both sides by T. And now we have what D is equal to. D is equal to TV, or velocity times time. Sweet. Now I can substitute. And so I can plug a value in. If D equals a T over, or T times V, then I can just plug in my T of 30 seconds. And I can multiply it by 100 meters per second. Now notice my seconds are going to cancel out because one is on top of the fraction, the other's on the bottom. And so now it's 30 times 100. All right, so 30 is equal to 3,000, right? So now I'm traveling a distance of 3,000 meters. Does that make sense? So how many sig figs? Well, I only had one sig fig in both of these, so my final answer can only have one sig fig, which is what I have. So 3,000 meters is my answer. Does that make sense? All right, so how'd you do? Hopefully you got that one. All right, practice this one, see how you do on this one, and we'll pause and then come back. Pause, and we're back. All right, how did you do? Calculate the time. So T, oh, what just happened there? T is equal to question mark, and we're dealing with seconds here, so it's question mark number of seconds. And it says that you're going to finish a 2.6 kilometer race. Oh, my distance is equal to 2.6 kilometers. And I have an average velocity of 28 meters per second down the hill. Now, you should notice something really important right here, that one of them is in kilometers and one of them is in meters. And in order to go through with this problem, we need to make sure that we have these in the same unit. And so let's go ahead and convert 2.6 kilometers to meters. And so what we would do is we'd say, okay, for every 1 kilometer, we have 1,000 meters. And so now we get an answer of 2,600 meters is our value that we're going to plug into our equation. What's our equation? Well, we know our basic equation is velocity equals distance divided by time. We memorized that, right? And so what would it look like if we reevaluated it and solved for t? Well, then it would be t is equal to distance divided by velocity. So let's plug it in. And so now we plug it in. We say, all right, well, t is equal to distance, 2,600 meters, divided by velocity, which is 28 meters per second. My meters cancel out, and we plug it into our calculator. We say 2,600 divided by 28, and we get 92.86. And our value is going to be in seconds. But how many sig figs can we have? We can only have 2 sig figs. So we're going to have to change that. That 8 will round that 2 up to a 3. So we'd say 93 seconds is our final answer there. Okay? So how'd you do? Did you get it? I hope so. I bet you did. All right, so let's finish off now in this chapter. Let's finish off with talking about how we would graph motion. I've now figured out how to do these equations. Hopefully you've done a few of them now with me and they make sense to you. But how can we study speed by using graphs? Well, we are going to plot the graph and we're going to plot a distance versus time. We're going to put distance on the vertical axis and we're going to put time on the horizontal axis. Now the reason we're doing that is because if we do distance here and time here, we can do, if you guys remember what a slope is, the slope is the rise over the run, right? And so rise over run. And what that means then is that this is the same thing, distance divided by time equals velocity. So we're going to find out that when we plot a distance time graph, the line that we create, the slope of that line will actually be the velocity or the speed. And so this is so cool. It's so much fun to see this translate from the graph to real world and back and forth from the real world to the graph. Okay, so time is the independent variable. That's the x-axis. Distance is the dependent variable on the y-axis. And the slope is going to equal speed. Now let's look at these 3 graphs and let's just kind of talk about the motion that we might have here. You can see that a fast-moving car might have a steeper slope. Okay, let me change my color of pen here. That fast-moving car is going to have a steeper slope than the slower moving car. All right. Why? Well, I'm not traveling as much distance in that same amount of time, right? The slow moving car is going to have less distance traveled per time. And that's why it's going to be a lower line, because my distance, look, I only got to like 50 here, 55, something like that. Whereas here, oh my goodness, my distance was up in 100, right? I was way up there at the 100 point in just 3.5 seconds, whereas 3.5 seconds here, I was still down like at 35 or something, right? So I'm traveling less distance in the same amount of time. And so my slope is going to be flatter the slower I go. So what about this third graph over on the side? What is that trying to tell us? Well, basically try to describe the motion, all right? I'm traveling at a constant velocity here. And then I start to slow down. When my line is flat like this, look, my distance isn't changing even though my time is changing. So if my time changes but my distance doesn't change, that means I'm not moving anymore, right? My distance isn't changing, therefore I'm not moving, and so I've stopped. And so this is the place on the graph when the slope is 0. That means that you've stopped, okay? and the slope is 0. That means you stopped. And now if I speed up again, okay, I'm moving and going faster, and now I'm speeding up a little bit more. So now I'm getting a little bit faster. I'm covering more distance in shorter time. And so I'm speeding up. All right. That means that there's some acceleration there. If you see that there is a change in the slope, okay, if the slope changes, that means you have acceleration or deceleration. Okay, we'll talk about that. Not yet, but that's gonna come up. All right, so let's look at how we calculate it again. I just want to remind you how to calculate slope, distance over time, rise over run. And so we want to look at our vertical change. That's our rise. So we'd say, oh, well, that's 6 meters. How did I come with 6 meters? Well, remember, I went from 6 all the way up to 12, right? From 6 to 12, that was the total change. I said, what was my speed during this interval between 6 and 12 meters, right? So my meters changed by 6. What did my time change by? Well, my interval of 1 second here to 4 seconds here. So I had a total change of 3 seconds. And so that means I went 6 meters for every 3 seconds, which means that my speed in this interval was 2 meters per second. So you can see how you can calculate the actual speed by just looking at the distance over the time, and then you get the speed, right? Isn't that cool? That's the slope. All right, so let's look at a couple others. Well, actually, this is just going through what I just showed you. Okay, so there's the work for it, kind of written out. But if you understood what I just showed you, then you're good to go here. All right, well, isn't that pretty neat? I love that part. All right, let's see if we can actually graph one of these ourselves. All right, so we've got some time and then distance. Well, I don't have any distance values to plug in here. So let's assume that we had a little experiment and we were maybe rolling a ball, or maybe I was running or asking a student to run forward and backward. Let's just choose one of those. Let's just make it simple to start, and let's just say we're rolling a ball. And so if I start to roll a ball, let's say I'm at 0.5 feet, and that, starting at 0. We're assuming that at time 0, we're starting at 0, right? And so let's go ahead and give our value a 0 there. And then let's say after 2 seconds, it kind of got a slow start, 0.5 feet, but then it starts to speed up a little bit, okay? And now it's traveled 2, and now it's traveled 8, and now it's traveled 64, and now it's traveled 256. All right, so this thing is going faster and faster and faster, or is it, right? Let's kind of graph this and see what happens. If we start, and again, this is our distance and this is our time. We start at 0, and then it barely moves at all, okay? Barely moves at all in that first 2 seconds. So we're going to do a 10-second interval here. So 0, and then let's do 2, and let's do 4, 6, 8, 10. All right, so let's just kind of pretend like those are pretty regular. I'm not sure how regular they really are. And then on the distance, we've got to get all the way up to 256. Oh my goodness. And so let's just say we've got 20, 40, 60, 80, 100, 120, 140, 140, 160, 180, 200, 240, 220, 240, and 260. Okay, ish, right? Oh, 260 way up here. So in the first 2 seconds, it was like, still like barely, it was pretty much on the line still, right? And then after 4 seconds, it was just still like really close to the line. After 6 seconds, it still isn't even up to the halfway part, right there. And then at 8 seconds, oh my goodness, all of a sudden we went up to 64. And so 20, 40, 60, 4 would be somewhere like that, right? And so you come over here. Okay, maybe put a dot there. And then at 10 seconds, it's 256. So all of a sudden, way up here, all the way almost up to that 256. So what does that curve look like? Well, that curve is pretty much flat. And then all of a sudden, oops, I missed that line. Undo, undo, undo. Which button is it? I think I have a button over here that means undo, and I can't think of which one it is. Ah, not that one. Okay. I don't know where my underwear is. Almost sounded like I said, I don't know where my underwear is. That's not what I was trying to say. Oh my goodness, now I've really messed myself up. Can't even get my pen over there. All right. Ah, oh my goodness. All right. Sorry, folks. Undo's that bottom button. Okay. And oh my goodness. Display toggle. Yes. Oh my goodness. You are being so bad. It's not really being bad. Technology is doing exactly what it's meant to do. It's just me that can't figure out what's going on. No. Oh my goodness. Okay, there we go. And help me, help me, help me. All right. Let's try that again. Wow, you guys, that was really painful. Sorry that was so painful. All right, let's try it again. And all it was, I mean, it didn't really matter, but I just like I was supposed to be like right there, my little dot. And just, all right, so here I go. Man, pretty much flat. And then all of a sudden, go up, and then I shoot up, and then I shoot up even steeper and steeper and steeper. Okay, so this is a curved line. If I were graphing motion that was accelerating, you can see how my curve continues to change. We'll talk more about acceleration later. But what I want you to see is that is different than a consistent distance changing. So if I started at 0 and then I went 1, 2, 3, 4, 5, or let's say I started at 0 and went 20, 40, 60, 80, 100. So 20, 40, 60, 80. Where's my 80? I don't know where my 80 is at. Something like that. And then 100. Okay, so this should be basically a straight line. Pretend like I'm drawing a straight line here. I wasn't. I tried. Anyway, this is different. So this straight line would be constant velocity. Okay. And so constant velocity is going to be a straight line. And then if it's not constant velocity, then it's going to have some sort of change in the line. In this case, I have something that's not constant, it's accelerating. All right. So maybe this one's rolling downhill, or maybe it's a rocket that's blasting off or something. Okay. So I just want you to see how motion can be described on the graph, because to me, that is really, really, really fun stuff to see motion described on a graph, and that you could actually kind of have like a little story in your head about what's happening and how quickly this is changing. We can look at some other graphs, and it's kind of fun to think about what would happen in different situations. Like if I have a distance time graph here, and what if I have a line that goes downward? What does that mean? Well, that means over time, my distance is going, let's say I was at 10 and my distance goes down to 2. I'm going backwards, right? Remember we talked about the fact that you kind of have to think about the number line. And so if I have like a 0, and I could go forward or I could go backward, right? And so if I start at 10 and I go back to 2, then my line would look a little bit like this. Now it's constant velocity. In this case, I'm continually moving, at a consistent rate backwards from 10 to 2, 10 meters to 2 meters, right? Because these would be like little meter values, right? Little meters. What would it look like what would it mean if I were to see it kind of go woo like that? Well, you can see that I've changed my distance again. So I'm going backwards again, but am I going backwards at a consistent rate? No, I'm changing the rate at which I go back. And so at first I'm going back really fast because I cover a lot of distance in a short amount of time. And then I slow down and I almost then come to a stop. If I come to a flat line, I've now started, I go back fast to start, and then I kind of like slow down, and then I'm like stopping, right? Okay, cool. See, on this one, I don't really come to a stop, or at least we don't see. Maybe I hit a brick wall here and I'm like flat from that point on, right? But here you can see I kind of slow down. All right, so that's kind of the same thing. I might speed up and then slow down. Here I've come to a stop again. If it's a flat line, I've come to a stop. I started out fast and I slowed down and came to a stop. Flat lines are going to mean that you're back to a stop in this case, right? So these are all different ways that you can express things. Like what happens if I go like this, and that was supposed to be flat. I'm going to try that again. You know, it didn't look too flat. Not flat enough for me. Okay, we're going to, yeah, it's kind of flattish. What if it does that, right? So now what is that describing? I've got my distance is increasing, so I'm going forward, and then I stop for a long time, and then I go backward. You see what's happening there? And I go back to 0. I go back to my 0 meter mark from where I started. So I want you to be able to take motion and put it onto a graph. I want you to be able to take the graph and describe the motion that would make that kind of graph. Okay? Fun stuff, right? All right, so here are a couple different plots of different types of things and how quickly they move. What are the different speeds, right? So a cruising jet would be much faster than a race car or high-speed train, but a galloping horse is really slow comparatively. Wheelchair racer, person walking. You can kind of see some of the different speeds of these different things. It's kind of cool to see that. And if we look at the red line versus the green line versus the blue line, which line has a larger slope? Well, the one that's steeper, right? And so immediately we can tell that this red one is going to be the fastest, right? And the slowest is going to be the one that is the flattest, and so that's going to be the green. How could we calculate the slope of the red line? Well, let's just take points where they intersect. It intersects right here at 16. And so what's the total change? It goes from 0 to 16. So we have a 16 meter distance, right? And then what's this time? It goes from 0, and this is 4. And so it goes and does that in 4 seconds. So it means that we're traveling at 4 meters per second, right? That would be, what its speed or velocity is going to be, right? Could we really say it's velocity? No, because we don't have a direction. So we'd really want to say speed. Now, you notice that I keep using the same formula, V equals D over T, even if I don't have the direction. Well, just remember that you can use that formula. I don't care if you show your work for that formula, but just make sure that you know the difference, that if it's velocity, then it better have a direction. And if there is no direction like this, then your 4 meters per second would actually be called a speed instead of a velocity. All right. Well, if you'd like to take a brain break video, and we're stopping the motion, right? Break instead of B-R-E-A-K. You're welcome to watch this little video. And it's the Roadrunner and Wile E. Coyote. I'm not sure how many of you guys are familiar with that, but it's a classic cartoon action from my childhood. So if you want to go to that, you can watch that, see what the Coyote and the Roadrunner are up to. What would some of those motion actions look like, on a distance versus time graph? Like, think about the Coyote, when he runs into a solid rock. He's going from really fast, and all of a sudden he runs into a solid rock. So he's like, maybe he's speeding up, and he's getting faster and faster and faster, and all of a sudden he runs into the rock, and he's completely flat. Okay, what would that look like? So I want you to watch it. If you want to watch it, again, you don't have to. This is just for fun. But if you watch it, think about what would his motion look like? What would the Roadrunner's motion look like? What happens when the Coyote is just like running in place? Like he's like, woo, but he's not moving anywhere. And then all of a sudden he drops. Pew! There's something on this one where it has him kind of being like part of a spring. And what would that look like? I don't know. It's impossible to draw real physics here because the Coyote and the Roadrunner do not follow real physics. All right. Anyway, that's fun. Let's see what we've learned today as we review. Can we describe the similarities and differences between speed and velocity? Yeah, big difference, right, is that velocity has direction, speed doesn't. Similarity, same formula, distance divided by time. Calculate speed and velocity. We now can do this. We have the algebraic tools under our belt that allow us to do this. And then now we can do this, such a cool thing. This is going to come in handy in your future if you're taking ACT tests and things like that. Learning how to interpret graphs. This is a classic graph to be able to interpret distance versus time. Now you can look at a distance time graph and you can interpret and see that the slope is the velocity. And that, my friends, is magical and fun. I hope you had a good time learning about this today. Have a great day. God bless you, and be kind to one another.